This week we start our study of relativity. This is a theory of space, time and motion that is one of the great unifications in physics. If you look at the development of physics over time, many of the important theoretical developments have been about taking things that seem to be different and figuring out that they're actually the same. So, for example, the thing that made apples fall to the ground from an apple tree and the thing that kept the planets in orbit around the sun and the moon in orbit around the earth. Gravity. Newton's great realization. Two things that seem to be different, one earthly, the other heavenly, turn out to be the same. Electricity and magnetism. Heat and energy. Heat is just a kind of energy, a unification. The one that we're studying is the unification of space and time into something greater called spacetime. This is not part of our everyday experience. In that sense, it's like quantum mechanics. It can seem very abstract, but it's just because our experience of the world is really very limited compared to how the world actually is. That's the message of both quantum mechanics and relativity. The unification came about as a theoretical development based on some postulates that Einstein made. The first one was the principle of relativity, and this had been around for a long time. The idea is that physics doesn't depend on how you're moving. As long as everything that's relevant to the system you're trying to understand is moving in the same way, with uniform speed, then it doesn't matter that you're moving. So, for example, you can do an experiment on an airplane or indeed on a rocket, and as long as it's uniformly moving, you'll get the same result as if you did it on Earth. The overall motion doesn't matter. That idea had been around in some form or other since Galileo. Einstein just emphasized that it applied to everything, including electromagnetism, and his second postulate was the really weird one, and that is that the speed of light is always the same. Whenever you measure it, you get the same value. And that doesn't make a lot of sense at all with respect to everyday ideas and experience, because usually when we move relative to something, its speed changes due to our relative motion. But that's not true for light. And that's what leads to all the profound implications about space and time. It turns out that our experience of space and time is a subjective experience. There's nothing objective in the world that is space and that is time. They are part of a greater objective whole called space-time. Our particular experience of them, our particular subjective experience of them, is different depending on who we are, or more to the point, what we're doing. For example, how fast we're moving. So we have a movement from things that we used to think were the most objective thing that there was, namely space and time, the background for everything else, to them becoming a subjective part of our experience. So all this might seem pretty philosophical, but it turns out it matters. For example, in hospitals, electrons are accelerated to near the speed of light and they behave relativistically. They live in a world of space-time, not of space and time. And to make those machines work properly, you have to understand relativity, the subject we're about to study. The GPS system is based on relativity. If we didn't understand relativity, we couldn't have built the GPS system, except maybe by trial and error, but it would have been an expensive and difficult process. The fact is, we do understand relativity, and that understanding is an integral part of the GPS system working. A lot of heavy chemical elements have properties that are the result of the relativistic physics of the inner electrons, which are moving at a significant fraction of the speed of light. For example, the color of gold, the fact that your battery can start your car, they're all the consequences of relativity. And in a world where there was no relativity, gold wouldn't look at gold and your car wouldn't start. If you get the opportunity, please have a look at some of the simulations that are available, computer simulations of relativistic motion. They may help you deal with the abstractness of this material by giving you a simulated experience of what a relativistic world would be like.